In this tutorial, we try to address the common question, why does Lasso regression suppress the coefficient in linear regression? A brief review of linear regression, which you can find plenty of material from the textbook or online material, and I have a prior tutorial on this subject. Linear regression would predict a dependent variable based on some observation x. We assume that they have some linear relation, which is often true or at least a good approximation of a lot of relation in physical world and social events. The mathematical formulation is that y, the dependent variable, has linear relation with the variable x1 up to xp, and we have some epsilon. Now usually in linear regression, it is assumed to be a white noise of normal distribution. The linear regression problem comes down to find out the proper value here from the observations. It has mean square error formulation. That is, in linear regression, we try to find the best fitting line, right? So line fitting and mean square error is mathematically equivalent. There's some prior YouTube tutorial from my channel. So mathematically, we try to minimize what's called MSE, right? The mean squared error, where n is number of samples, y sub I is the actual output, and y hat here is the prediction. So the goal to find out the parameter that would minimize this quantity. Now, one common issue with linear regression is called overfitting, right? That's an important concept. This is when a model learns the training data too well. Now, including the noise and outlier from the data. If you change another set of samples, the performance may decrease. Now, there are techniques to prevent overfitting. Now, one common technique is what is called regularization. In the ridge regression, in addition to the mean square error here, we add another quantity here, coefficient itself. We try to have L2 norm, the vector length of the beta, which is coefficient vector in the multi-dimension setting. Here, lambda is a parameter you can tune. So it controls the amount of shrinkage applied to the coefficient. Intuition here is that if beta is too big and this quantity is big, since you want to minimize this error here, you try to have a solution where beta itself won't be too big. Okay, this kind of suppress overfitting. So it's really important to understand the intuition behind the math. Lasso regression, however, is another technique, and the difference here is the quantity here is L1 norm. L1 means in multidimensional setting is the sum of the absolute value of the beta. So here again, using lambda to control the amount of shrinkage. Intuition is the same. The quantity here, you try to have a penalty for the solution that has too large beta value or too large of absolute value of beta. Here lambda is a parameter you can tune. It controls how much suppression you want to introduce to your original model. So it controls the trade-off between the fitting the data well and keeping the coefficient small. It has a better performance for other datasets. Too large of lambda maybe overly penalize the coefficient, where too small you may lose the value of the regularization, and then you come down to the problem of overfitting. Now, how to choose a proper lambda? There's a technique to cross-validation will allow you to find out the optimal lambda. In another Python package like scikit-learn, there are built-in utilities for cross-validation. Now, of course, when we say lambda, which is a parameter to control the regularization, in Python packages, sometimes we say alpha. So lambda and alpha could be interchangeable in a certain context when we talk about regularization parameters. The learning objective here is to understand why Lasso suppresses some of the coefficient. This is the link to the YouTube channel on other tutorials on machine learning. and stats, and there's some copyrights. Okay, you can free to play with it, but just make sure you cited the source. This is like a generic linear regression setup, right? There's some background as we covered here is cost function for regularization for lassos. We're going to add the absolute value, which is L1 norm, and for the ridge we're going to use L2 norm, and in the literature we use lambda here. In the Python we use alpha. This is a parameter to control how much shrinkage we're going to allow. Again, this is covered in the earlier slides. And we're going to have two observations. Now the second one has a small contribution to the observation y, and this is error term, which is a standard linear regression formulation. Right? So here's the code to generate the data with the packages for the random. We set the random state so that when you rerun this experiment, you're going to have consistent results. That's just a good technique to use. All right, let's run through this notebook here. So we're going to look at Lasso and Ridge regularization with L1 and L2 penalty term to MSE. This is just to generate the data with initial small sample size. We just to make sure it makes sense. And this is the actual value here. The Colab provides some other visualization tool. If you want, you can click on that. So we're going to run the regression with a small sample size first. Let's say 200 samples. Okay, we're going to regenerate the data with 200 samples. We're going to choose alpha value to be 0.1 here. We're going to try two different regularization, and those are supported from the linear model module from sklearn. When you call this a fit function, it will run the regression and it will calculate the coefficient for you. You're going to have the predicted value so that you can evaluate the mean squared error here, right? I have a function here is also from the package, right? The mean squared error calculation. We're going to print out the coefficient here. So this is the results. Yeah. So when we look at the results, notice that here in the lasso you have 0 here, the suppression, right? And in the reality, the second parameter is small, right? The true value is 0.2. In lasso there's 2.35, and here 0. Here we have 3.4, 3.9, and that's beta 2 is non-zero, right? So the performance of both MSE are really close. So in this case, the L2 norm gives a slightly better performance, right? In the ridge regression, shrinks the coefficient towards 0, but does not set them to 0. In the lassos, is actually the x2 is 0, right? Now we're going to plot the contour. Remember, contour line is where the loss function or the function we try to minimize has equal values, right? That's called contour line. Really useful in a lot of analysis. So here, there's some utility function to compute the MSE, the norm, right? L2, L1, and we're going to plot the value for different range of beta 1 here and beta 2. We're going to try to calculate MSE, L1, L2 for those values, and then we try to plot it, right? So I'm going to skip the details here. So let's run that. And notice that since beta 1 and beta 2 are different range, we can change the scale here. For example, let's say this maybe make it smaller, because this different scale, right? Looks different than earlier, right? Because beta 2, the scale is different. And this is like from -5 to 5. This is from -2 to 2. If you want to make it the same, or you can play with the same quantity here. Let's say 1 to 5, right? Make it consistent here. Okay. So equal scale here, you're going to have similar results, right? That's the true value here. That's for the MSE regular one, and that's for the square one is for the lassos, and L2 norm is green one, is the smooth one. Okay. So in the visualization earlier, what we learned is that we learned different contour shape for MSE loss and for L1 and L2. Okay. And now let's rerun the experiment with maybe a bigger sample size, let's say 10,000. The only thing we change is here. Let's run that. And let's print out the parameter here in terms of MSE. So in both cases here, the ridge get a better representation, right? And in this case, it's also suppressed to 0. So which means our models are consistent in both cases. There's some analysis here I'm going to skip. And I encourage you to try this, but with a different data set. The famous data set is Boston housing data set. So I have the outline of the project, and please try to do it, and you can share your results in the video comments. All right, thank you. As we see in the Python experiment, the L1 will promote sparsely in the coefficient. That is, it will lead some coefficient to be 0. They're going to disappear. Okay, so that's very useful in the feature selection sometimes. L2 does not. Now, it's really important to understand again the intuition, right? So imagine we have the two parameters, beta 1, beta 2. It's actually good to understand the contour of the cost function, because the cost function here is mean square error plus the penalty term, and we try to minimize that. So when we trace the contour line, you're going to know where the minimization solution is. So in our lab, this is the contour line produced. The regular one is MSE for the blue one, and for the squared one is Lasso's, and for the green circle one is the ridge regression. Right, for the L2 norm, as noted here. L2 penalty is a circular constraint. So the coefficient here are found where the circle first meets the loss function contour. Due to the smooth nature, it shrinks coefficient but does not force any to 0. L1, the penalty is actually diamond-shaped constraint, so which often touches the loss function contour, making some coefficient exactly 0. In this diagram here, the dotted line here, right? So here, this is optimal solution here, and it's close to 0. So notice that this always touches the axis here. And this is two-dimensional. It will have similar behavior in multiple dimensions. All right. So that's the intuition. So L2 norm will penalize large values, making it reluctant to let individual coefficient grow unless it's in reducing the unregulated loss. So L1, growing linearly with coefficient values, it can reduce coefficient to 0 more readily. So earlier geometric interpretation allows us to understand the different behavior of L1 and L2. So L1 non-smoothness and the diamond shape here, we're going to lead to a sparse solution where some coefficient in the linear regression becomes 0. For this and other math and machine learning topics, please like, share, and subscribe to the channel.